Let's do an example on calculating center of gravity and gravitational torque. Gravitational torque just means it's the torque on an object due to the force of gravity on that object. Remember, torque is always um, due to a force that's causing an object to potentially twist, and gravity is a force acting on an object, so that could cause an object to twist. If I try to balance this thing on my finger, if the gravitational torque is through the pivot, it won't. If the gravitational force is through the pivot point, which is where it's touching my finger at the bottom here, it won't fall. But if it's over on the side, there's a force of gravity acting down, which has got a lever arm, which will cause it to rotate. So that's just all we mean by gravitational torque. Let's do an example. This is from the end of the chapter, chapter 7, number 38. It's two parts. First, we're going to find the location of the center of gravity. Then we're going to calculate the torque. So what we have is two beams connected to each other in an L shape like this. And the length of this beam is 1 meter, and the length of the horizontal beam is 2 meters. And we are told that the mass, drawing a little pivot point there in advance, that the mass of the vertical beam is 15 kilograms, and the mass of the horizontal beam is 25 kilograms. And the first part of the question is, what is the center of gravity for the two beams together? Where is center of gravity for these two beams? To answer this, we need to remember first that the center of gravity for a uniform object is in the geometric center of that object. So again, taking my pen, if we ignore the tip here, if this is uniform distribution of mass, then the center of gravity will be at the geometric center of it. So just exactly halfway across this bar. So the center of gravity of each beam is at the center of each beam. So we can consider each beam to be a point located at its center. So that means that our L-shaped beam becomes something like this, where here's my origin. So I'm just gonna, I'll try drawing in a dotted line where the beams are, but these points are at the center of each one of those beams, and to calculate the center of gravity for this thing overall, I can just use those 2 points. So this one I'll just call, that's like M1, which was 15 kilograms, and this one I'll call M2, which is 25 kilograms, and I'm putting my origin at the corner here. I could put the origin anywhere I want. Okay, it's an arbitrary decision. It's like when we're doing kinematics and things like that. You can decide where to put 0. Okay, in principle, it'd be easiest to put the 0 point at the center point of one of these objects, because then the position, the coordinates of that object are 0, and so we don't need to worry about that when we're calculating the center of gravity. The reason I'm putting it down here in the corner is because part B of this problem asks for the gravitational torque about an axis located at that point. And so we're going to be using that point in part B. If I wasn't using part B, I might have defined my origin to be like in the middle of this horizontal beam. And then the center of gravity for that horizontal beam is just 0. And that makes the calculation of the overall center of gravity a little bit easier. But since we're going to be rotating it around this corner later, I'm going to define that to be my origin. So the x position of the center of gravity is just the x position of mass 1 times m1 plus the x position of mass 2 times m2 divided by m1 plus m2. The x position of mass m1, if we define x to be horizontal and y to be vertical as we usually do, the x position of mass m1 is 0. Okay, it's on the y-axis, it's not left or right of x. So x1 is 0. x2 is halfway along that horizontal bar. That horizontal bar has a length of 2 meters, so x2 is 1 meter. It's at the midpoint, right? That horizontal bar is like this pin. If it's 2 meters long, the midpoint is 1 meter away from the origin, and so that's the position of x2. So that gives me xcg equals 0 plus 25 times 1 divided by 25 plus 15, which is 40. So that gives me xcg equals 25 over 40, which I should have been able to do in my head, but give me 1 second. I think it's that's about 0.6. Oh dear, my computer is being slow. Or something weird is happening and my computer has, sorry about that. 25 over 40 is 0.625 meters. So that's the x coordinate of the center of gravity. The y coordinate of the center of gravity is y1 times m1 plus y2 times m2 divided by m1 plus m2. The y coordinate of mass 1 is, remember, mass 1 is the vertical beam. So the y position of that mass is at the midpoint of that mass, halfway up. So y1 is 0.5 meters. y2, that's the horizontal beam. It's on the x-axis. It's not displaced up or down. So y2 is 0. So that gives me ycg equals 0.5 times 15 plus 0 divided by 25 plus 15, which is 40. So that gives me 7.5 over 40, which is, should be able to do that faster this time, 0.188 meters. So those are the x and y coordinates. The center of gravity is at 0.625 and 0.188 meters. And that makes sense. It's low because most of the mass is in that horizontal beam at the bottom. Now, part B of this problem says, what's the gravitational torque around axis at the lower left corner? So let's do our torque calculation here. So somewhere here is our center of gravity, actually. It's a little bit more like that. There's our center of gravity. And here is our axis or pivot point. And what is the gravitational torque? I put a little W underneath the tau to indicate that's the torque due to the weight. So what the center of gravity does is tell us where we can consider the weight force to be applied. So the weight of this whole big L-shaped thing is applied at the center of gravity, and we can calculate the torque is a lever arm times a perpendicular component of the force, or a moment arm times the total force. And so for this particular one, I think the easiest way to calculate that force, we can draw r is this distance, and then I would need to calculate the component of the force that's perpendicular to r, but it's easier to just calculate the total force times the perpendicular distance from that force line to the axis. So remember, there are these two ways you can calculate torque. One is by taking the line from the pivot point to the point where the force is applied. Then you could find a component of the force perpendicular to that line. So then I would need to find a component of W that's perpendicular to that line. That's going to end up with a triangle similar to this triangle I've got over here. And I'd be using these 0.62 and the 0.188 as the legs of that triangle to figure out that angle. Alternatively, I can extend the line through the force vector and find the point on the force vector that is closest to the pivot point. Then draw that line over from the force vector to the pivot point and use that distance. This is the thing that we're calling our perp. It's called a line of action in the book, but the reason we're going to use that is we already know how big that is, because that's just the x coordinate of the center of gravity. F is the weight, which is the total mass, 40 kilograms times 9.8 meters per second squared, and r perp is just this distance from the pivot point over to that force vector, and that is the x position of the center of gravity, so that's 0.625 meters. That then gives us, I want to use another piece of paper, even though it's virtual paper, not cutting down any trees. Oh dear, sorry, let's shift this up so you can see it. Okay, the force is 40 times 9.8 meters per second squared. Our perp is just the x position of the center of gravity. That's how far it is from the axis point over to this arrow that I've drawn from the center of gravity straight down, which is the direction gravity points. So then that gives me torque equals 40 times 9.8 times 0.625, and that is 245 Newton meters.